Alright, so this is the second set of notes, and this is going to be about normal distributions and the empirical rule. If a histogram is roughly symmetric and unimodal, what we do is we call it a normal distribution, or sometimes we just say that it is normal. So what are some things in the real world that just have a normal distribution? Heights of adult males. If you sampled heights of adult males, it would be normal. The life of a light bulb is normally distributed. Scores on an IQ test. Now, this doesn't happen naturally. What happens is the test scorers actually they normalize the test scores, and so they take the results and they force a normal fit into the answers or into the scores that they report out, and then they base a score of 100, which is a quote unquote average. They base that on what the scores were that they received, and so as a matter of fact, about every decade, the average score for an IQ being 100, it actually gets raised up several points. I think it tends to go up about 10 points every decade or so. And so they force IQ scores into a normal distribution, but they use a normal distribution in order to generate the statistics where they say, oh, I'm in the top 15% of intelligence in the human race because I scored on the top 15th percent of the IQ test that's based on the normal curve. Annual rainfall is another example, and so on and so forth. So some properties of normal distributions. You can see a bunch of them right here, and so we can see that they are all bell-shaped. They are all symmetric about the mean. And remember, that is usually abbreviated with x bar, or possibly with mu, so it's symmetric about the mean. They are unimodal, meaning they have one mode, they have one thing that happens most often. They have one peak, so they are unimodal. And they also all have an asymptote at y equals 0. So you can see that they're all flattening out right here at the bottom. They don't ever actually touch 0, but they all kind of flatten out down there. So the area from the average, from the middle here, over to infinity, because remember, this is an asymptote, it never quite gets there, but if you can go to infinity, that would be half of the data, and so half of the data is on the other side. So 50% is the area underneath the curve from here this way, and the other 50% goes here to negative infinity. So each of these graphs is normally distributed, and so what are some things that we notice about the spread? Notice that this one is spread farther out, so this one would have a larger standard deviation. This one is kind of grouped all together close to the mean. This would have a smaller standard deviation, but in either case, we notice that they are spread out symmetrically. And again, we've got the mean x bar and the standard deviation s, and we're going to use these two statistics to create normal distributions. So there's an example here. I'm not going to read it to you. You can read it to yourself, and you can resume the video when you are ready. 213 students are the ones, that's the sample population, and then we can see the information is gathered up here. Now we're going to just ignore this as part of the graphic that we couldn't take out, but we're not going to use that as we do our calculations. So we're going to be looking mostly at this table. And then this histogram is created based on this table. And if you look really closely here, this is 4 and this is 8. So each of these histogram intervals is an interval of 2. The space of the interval is 2. And so like 1 and 2 are together on the histogram. 3 and 4 are together, and so on. Question A, does this distribution appear to be normal? Yes, in fact, it appears to be normal-ish. It doesn't have to be perfect. But it is bell-shaped, it is unimodal, it is symmetric about the mean here. The mean is 10.221, and it has an asymptote at y equals 0, meaning that these values as we go out here would be approaching 0. we want to figure out how many scores fall within one standard deviation of the mean. Well, the mean is 10.221, and one standard deviation is 3.859. So if we want to go one standard deviation on the positive side, that would be this way. We're just going to add the standard deviation. So we're going to have 10.221 plus 3.859. So the upper end is going to be 14.08, and the lower end is going to be the mean minus the standard deviation, which is 6.362. Okay, so the lower end is 6.362 and the upper end is 14.08. Question C, we want to see how many of the 213 scores fall within this range right here. So we're just kind of estimating here. We're kind of looking at in general, what is this? So we're going to call this about 6 because we don't have decimals in our table. So we're going to call this 6 to 14, and we want to see how many scores fall between that interval from 6 to 14. And so we can count up. Here's 6 to 14, and we're going to add up all of these numbers right here. So 13, 15, and we get 159. So 159 of the 213 scores. So 159 fall within that range. What proportion of the 213 scores is this? You'll do 159 divided by 213, and we get about 74.6%. Determine how many of the 213 scores fall within 2 standard deviations. Well, one standard deviation was 10.221 plus 3.859. So 2 standard deviations is add one more standard deviation to it. So that's going to be from about 18. We'll call that about 18 as the upper end. And then if we take 10.221 and we subtract 2 standard deviations, we get about 2.5. So we will look now at adding up all the numbers between, we'll call this from 2 to 18. And so now we're adding up all of these numbers all the way from 2 to 18. And some of the table didn't copy completely, so we don't actually have that number over there for 18. But if you look on the chart down here, so this is 16, so 17 and 18 are right here. So there are a total of about 10 that fall between 17 and 18. So we're going to say that this 18 number is going to have about 3 in it. So that the total of 17 and 18 is this total column right here is about 10. So if we add all of those numbers up, we have the 159 from that middle group. So I'm going to leave that 159 there and just add the ones that we are combining with this. So we'll start with the 1 plus 5 plus 7 plus 12. So that takes care of these 4 right here. And then we'll also add these 4 out here. So plus 8 plus 4 plus 7 plus 3. So we get a total of about 206. And again, the proportion out of the 213 is about 96.7%. And then how many of the scores fall within 3 standard deviations of the mean? So 3 standard deviations would be 10.221 plus 3 times 3 standard deviations. That would be 21.798, and 10.221 minus 3 standard deviations is negative 1.3. Notice that the values in our table only go from 1 to 20. So all of the values in my table are within this interval. So 100% of the scores will fall within 3 standard deviations of the mean. So now let's look at what the normal, if something is distributed perfectly normally, what it would actually look like. So in the normal distribution, what we have is, this is called the empirical rule. Sometimes it's called the 68, 95, 99.7% rule. About 68% of the data falls within one standard deviation of the mean. So you can see that right here. If this is your x bar and you add one standard deviation and you subtract one, then 68% falls between here and here. That means that you have 34 on either side of the mean. So 34 here and 34 here, and together that gives you 68. Well, if we want to do between two standard deviations, then that ends up being a total of 95%. So if you take that total of 95% and you take out the 68% that was in this middle part, and then you cut what you have left in half, you'll see that each of these sections is going to be 13.5. So if you add up 13.5, 34, 34, and 13.5, you will get 95%. So 95% of the data will take place right there. And then if we extend it out to be one more standard deviation, we're going to find that 99.7% of the data happens between here and here. So there's a very, very small percentage that occurs on the tails that are bigger than or smaller than 3 standard deviations away. Okay, so again, if 95% of the data goes from here to here, and you took out, or sorry, 99.7 goes from here to here. If you took out that 95% and you cut what was in half left, or cut what you had left in half, then you'd get what was in each of these little pieces right here. And you'll find that that ends up being 2.35%. So if you add up from here over to here, you'll get 99.7. And so you can see the other 0.3 is distributed right here at the very tails. Usually you don't go beyond 3 standard deviations, so that it's sufficient to do 68, 95, 99.7%. All right, so let's look at example 2. Let's sketch and label a normal curve with a mean of 0 and a standard deviation of 1. So the mean is 0. We're going to go up 1 and down 1, and up another 1 and down another 1, and then we'll do it one more time, up another 1 and down another 1. And so my normal curve needs to be, remember, it needs to be symmetric about the mean. So you can see here it's symmetric about the mean, and we're going to put the percentages under the curve here. So remember that one standard deviation away is a total of 68%. That means there are 34% here and 34% here. Okay, and then from here to here is 95%. So if you take 95 and you take out the 68 that we've already used, you're going to be left with 27%. So between here and here, we need to split that 27% in half. So they're 13.5% here and 13.5% here. And then you're going to do a similar thing with, we know that from 3 standard deviations away we have 99.7. So if you do 99.7% and you take away the 95% that we've already used on these 4 other sections on the inside, then you are left with 2.7%. Sorry, 4.7%. And if you divide that by 2, you get 2.35% over here and 2.35% over here. Alright, let's look at example 3. Again, you can read the problem yourself. We want to find the percentage of seniors scoring between 390 and 590 on this SAT test. We're told that the mean is 490 and the standard deviation is 100. So 490 is going to be the mean. One standard deviation away is going to be 590 and 390 here. So when it's asking what percentage of seniors scored between 390 and 590, it's saying what percentage of seniors were within one standard deviation away. Well, we already know the answer to that. Every normal curve, if it is distributed normally, then 68% of the data is going to fall within one standard deviation. So the answer to this part is just 68%. One student scored 795. So let me answer that over here. So 790 790 would be 3 standard deviations away. 795 would be greater than three standard deviations away. And based on our chart up here, we know that if we are more than 3 standard deviations away, he is in the top 0.15%. So he scored better than 99.85% of everyone who took it. He scored in the top 15%. He or she. All right, and then part C says that this university only wants students who were in the highest 16% of scores on the test. So you need to, it's kind of better to start with the middle and say, well, 50% is here. So if we want the top 16%, we need to get until we've used up 84%. So so 50% is down here. Is going to be from the mean and down. And then if you add another 34, so you do 50 plus 34. So right here and this way is going to be 84%. 84% of people will score 1 standard deviation and less, because 50% is this way, so this is 84. So if you want only the highest 16%, you want the people over here. So they would need to have 1 standard deviation or more. They would need to be at least 1 standard deviation away from the mean in the high direction. So remember, with this example, 490 is the mean, so 1 standard deviation is 590. So these students would need to score greater than 590 to even be considered, because that would put them in the top 16%. All right. Example 4 has the mean is going to be 63.6, so we'll put that right in the middle, and the standard deviation is 2.5. So we can do 63.6 plus 2.5 is 66.1. We can do plus another 2.5 is 68.6, and plus another 2.5. Again, usually 3 standard deviations is well beyond what most people need. And then we can go the other way. We can subtract 2.5 and subtract 2.5 and subtract 2.5. So if you saw this, sometimes you'll see the notation here, and it'll say the normal, and it'll give you the mean and then the standard deviation. So it'll say 63.6, comma, 2.5. Big N standing for normal. So that's what this one would look like. What percentage of women are between 1.6 and 61.6 inches and 66.1 inches? Well, 61.1 is here and 66.1 is here. So they're asking what percentage is 1 standard deviation away from the mean. And based on the empirical rule, we know that the answer to that is 68%. So between 61.1 and 68.8. So 61.1 and then 68.6 right here. So there was 68% right here. And then remember, this was 13.5%. You can flip back to here if you need to see this. So this was 13.5 here. So 68, 1 standard deviation away, plus we need to add another 13.5. And you should get 81.5% right there. What percent of women are between 63.6 inches and 68.6 inches? So now we're going from here to here. So we know that this is 13.5 over here, and this is 34% right here, and so we can just add those up. So 34 plus 13.5, and you get 47.5%. What percent of women are between 58.6 and 63.6? Well, that is asking for the exact same calculation just on the other side. So this is 13.5 and this is 34, and so that's also 47.5. And then how short are the shortest 2.5% of all women? So if we want the shortest 2.5%, then we are on the small side of right here. So remember, we've got 95% of all women fall within 2 standard deviations away. So 95% are from here to here, which means there's 5% left over. So 2.5 are going to be on the tall end of, we'll say, normal, and then the other 2.5 are on the short end of normal. So how short are the shortest 2.5%? Well, they're going to be from this number and less. So they're going to be less than 58.6 inches tall. So for example 5, we need to be very careful with reading these two carefully to be sure that we are doing the exact thing that they're asking for. So the mean is 30 ounces, right here. This is the mean. So we'll call that kind of our 0 point. And then the standard deviation is 10. So this is minus 1 standard deviation, and then over to 10, that's going to be minus 2 standard deviations. 40 would be up 1 standard deviation, and 50 would be up 2 standard deviations. So the first question is, how many bags have a weight that is less than 2 standard deviations below the mean? And initially you might want to pick just this part that's past 2, but that would be more than 2 standard deviations less than the mean. So we want to be less than the mean. So we want to be on this side of the histogram, but we want to be less than 2 standard deviations below the mean. So right here is when I hit 2 standard deviations. So we want to be within 2 standard deviations this way. So these numbers are going to be the ones that are 2 standard deviations or less away from the mean in that less than direction. So we're basically going to add up all these. Now we are kind of estimating the graph here, so when you look at it you might get slightly different numbers than I do. I'm going to call this one 5, I'm going to call this one 10, this one's 17, and I'm going to call this one 27. If you got slightly different numbers, that's fine. We're just going to add these all up. So 27 plus 17 plus 5 plus 10, and you get 59. So there are about 59 bags that are less than 2 standard deviations below the mean, on the below side, and then they are within 2 standard deviations. The second question says, estimate the number of bags that have a weight that is more than 2 standard deviations about the mean. So we want to be farther away than 2 standard deviations, and it's not telling me if I'm less than the mean or more than the mean, so it could be on either side. So I want to be sort of outside of 2 standard deviations. So if this is negative 2 standard deviations, and at 50 this is positive 2 standard deviations, then the things that are outside are just going to be sort of these tails over here. So I'm going to say that this one's about 2 and this one's about 3, and so there are about a total of 5 bags that are more than 2 standard deviations about the mean. More than being farther than 2 standard deviations away. About meaning it could be on either side.